All right. Sometimes it takes a couple of seconds for the live stream to pick up, but I believe that we should be live now. All right. Yes. And hello, everyone. Welcome to this live event. My name is Maria, and I'll be your host today. So go ahead and say hi in the YouTube chat. So this event is to celebrate the launch of our brand new course on audio transformers. And as most things Hugging Face does, the course is open source, free, and created by a team that has expertise in the domain and a drive to share knowledge and democratize machine learning. I am proud to be part of the team that has brought to you this new course. And we're also joined by two other team members. So we've got Sanchit, say hello. Sanchit is a machine learning research engineer at Hugging Face. And we have VB, who is a machine learning developer advocate engineer. So if you have any questions about the course, drop them in the chat. We are going to try to stay on top of them, keep up with your questions. And today we have officially launched the course. So the first couple of units are already available, and they teach about the specifics of audio data, common audio tasks. And over the next few weeks, we will be releasing more units, and you'll learn about transformer architectures, which are commonly used for audio tasks, and nuances of selecting appropriate data, pre-trained models, fine-tuning your own models for classification, for speech recognition, text-to-speech, and much more. So today, we have invited some amazing guests to help us celebrate the launch of this course. And our guests will share their insights, experiences, nuggets of wisdom to hopefully inspire and motivate you to learn and build your own things. And so let me quickly introduce our speakers. We have Seokhwan Kim, say hello, who is a principal applied scientist at Amazon Alexa AI. Let me bring up my notes so I don't mix anything up. So prior to joining Amazon in 2019, Seokhwan conducted work in natural language understanding and spoken dialogue systems, where he was an NLP research scientist at Adobe Research and a research scientist at the Institute of Infocom Research in Singapore. Seokhwan completed his PhD work at Pohang University of Science and Technology in Korea, and he has authored numerous peer-reviewed papers in international journals and conferences. His recent research has centered around knowledge-grounded conversational modeling, and Seokhwan actively contributes to multiple research communities. We are thrilled to welcome you, and we are looking forward to your talk, which is going to be first today. Next, I'm happy to introduce Brian McFee, who is an assistant professor of music technology and data science at New York University. He received his Bachelor of Science degree in computer science from the University of California, Santa Cruz, and master's and PhD degrees in computer science and engineering from the University of California. University of California, San Diego. His work lies at the intersection of machine learning and audio analysis. He is an active open source software developer and the principal maintainer of the Librosa package for audio analysis. And when you start working through the course, in the first unit, you will get your hands on using this package. So Brian's talk is going to be very helpful for you to get to know the package a little bit better. So these are the introductions. Thank you, everybody, for joining us. We are happy to see you. We are happy to be able to share the presentations from our invited guests. And feel free to go ahead and drop your questions to us or to the speakers in the YouTube chat. Um, we want this to be a bit more interactive, so there will be presentations, but after the presentations, we have reserved some time for questions, for discussions, for opinions. So everybody welcome to post their questions in the YouTube chat. If you are on Discord, you can also start discussions there. And yes, with that, I'm happy to give the stage over to Seokhwan. And let me just bring the slides and make sure that everything is ready for our first presentation. So give a warm welcome, say hello, and we're ready to start. I'm just going to remove everybody else from the screen so that the stage is all yours.
Okay. Yeah. Thanks, Maria, for the great introduction. And yeah, thanks for having me. And first of all, congratulations for launching a new audio transformers course. And I'm Seokhwan Kim from Amazon Alexa AI, and today I'm going to present our previous work. And actually, this is a kind of the use case of transformers library to process the audio files, basically the speech files. And the title of this talk is How Robust Are You? And Evaluating Task-Oriented Dialogue Systems on Spoken Conversation. And as you can see from this title, so I'm basically a dialogue researcher, and my background is mostly for the NLP, not for the speech, but we needed to address some speech-related problems in the dialogue systems. So yeah, this work was a joint work with my team members Yang, Alex, Kartik, Benham, and Dilek. And yeah, so the main motivation of this work was that, so there have been many the public data sets becoming available for dialogue research and dialogue system development. But the thing is that most of the data set were written conversations, because the main the way of collecting the dialogue data is through the crowdsourcing. And usually we launch this kind of web page to collect the text, the responses or text, the written text conversations from the crowd workers. And recently, with the advancement of the large language models, many people try to generate or augment this kind of dialogue data using the generative large language models. But here, the result from the large language models are also the written conversations. So yeah, that was the background that we had for this work. And yeah, here is one example of written conversation. And as you could see here, so all the utterances, all the text from the speakers are clearly written, so grammatically perfect, and so it looks okay. But when we consider some practical applications of spoken dialogue systems, so there should be some gaps between the written text and the spoken languages. The first of all, there is some differences in the way of writing and way of speaking. And in the spoken conversations, for example, from our daily conversation, we use so many disfluencies like this. So, hi, I'm looking for a place at or something like that. So that is not happening in the written conversations that we collect from the crowdsourcing or larger language models. So yeah, this is one the major differences between written data and spoken data. And another thing is that, so to build a system to handle the spoken inputs from the users, so we need to use the automatic speech recognition. And sometimes the automatic speech recognition produce some noisy recognition result like this. The actual one is price range, but that could be misrecognized as pressure engine, and the parking cost could be also misrecognized as a different word with the different meaning. So yeah, this kind of the ASR errors. So that is another issue in handling the addressing the spoken inputs in developing the spoken dialogue systems. So to address the challenges in such spoken conversations, we try to set up a new benchmark task. And this benchmark task includes two main tasks. The first one is dialogue state tracking, which is a traditional problem in dialogue research. And the other thing is the knowledge grounded response generation, so which is a relatively new task, but that has been recently widely studied in the dialogue research field. The first dialogue state tracking task is like this. So I think the animation is not working. So, but anyway, so here you can see that at the end of this conversation, the user's goal is to find the hotel in Fisherman's Wharf in San Francisco, and the user changed the preference for the price range from the I think from moderate to the expensive. I think yeah, the originally the user asked the moderate price range, but changed the price rate, changed their mind from moderate to the expensive. So the goal of dialogue state tracking is to capture this kind of changes and this kind of the users the preference or user's goal at each moment. So once this dialogue state is predicted in the structured representation like this by the dialogue state tracking model, so this information is used to find the relevant information from the domain API or database. In this case, the domain API is the hotel search API or something to generate the next response by the system and continue the conversations to achieve the final goal. So yeah, that is the an example of the multi-domain dialogue state tracking problem. That is the first task that we had in our benchmark. And the second task is knowledge-grounded dialogue modeling. For this one, so this was introduced by our team, and we organized the previous track in 2020 under the 9th Dialogue System Technology Challenge track. And for this one, we defined 3 subtasks. The first one is knowledge-seeking tone detection, followed by knowledge selection and knowledge-grounded generation. And this is an example. The motivation here is that in the previous dialogue state tracking task, we assumed that all the dialogue state can be represented as a predefined dialogue state representation, and the information is available. The relevant information to the dialogue state is available from the database or the API. But in practice, there could be some requests from the customer, from the user, which is out of the scope from the API or out of the scope from our dialogue state representation. So in this case, but we know that usually this kind of information is available somewhere in the web. For example, the hotel website or hotel booking the website, so we can find some information in multiple different formats. Like, for example, for the FAQs, some FAQs include this kind of information like the parking costs or something. So the goal here is to goal of this task is to decide whether we need some external knowledge beyond the API or database, and so once this turn detection is done and a given turn is predicted as the knowledge seeking turn, which requires the external knowledge access, so we go to the knowledge selection to actually retrieve the relevant knowledge from the knowledge candidates. And then finally, we generate the responses grounded on the selected knowledge from the previous task. So that was the definition of the second task. And to study these 2 tasks on the spoken conversations, we actually collect the spoken human-human dialogues about the San Francisco content for the hotel, restaurant, and the attraction in San Francisco. And this data was collected by pairing two participants. One person for each session was playing a role of a user. And for the user side participant, we provided a set of specific goals, like so what a kind of attraction or what kind of hotels the user is looking for, and so some booking details as well. And for the other side, for the agent side, the agent had the access to the domain database and all the knowledge about hotels and restaurants and attractions. And the agent lead the conversation to provide the information requested by the user. And yeah, this part is related to the Hugging Faces Transformers library. And so as I mentioned before, I'm not a speech guy. So I actually had no idea how we can translate or transcribe these human-human the conversation recordings into the ASL result. But at that time, the Hugging Face Transformers the released the WaveTech 2.0 support. This is a pre-trained model to get the representation from the speech audio files into the vector representation, and the ASL result can be decoded based on the representation, the embedding representation. And we fine-tuned the WaveTech 2.0 pre-trained model on the 960 hours of Libri speech. So originally we tried this pre-trained model itself, but there was some gaps between this training data set and our data set, because this Libri speech was the kind of the audio book. So a single person read the book, and that recording was included in this Libri speech. But our data set was dialogues between two people, and the content were very different from the book content. So we fine-tuned with the 10% of our recordings. So all these fine-tuning and the decoding, all these things were done using the Transformers library. And the performance-wise, it achieved around 26% WER. So that was quite high, but so it was kind of by purpose, because we wanted to evaluate the robustness of the dialogue models against such high ASR noises and ASR errors. And you can find the wave-to-vect details using the Hugging Face from the QR code that I put on this page. And yeah, this is yeah. So I see a question about the so yeah, that yeah, question is about the WaveTech, and so what we used was the original version of the WaveTech. So I think so I don't know whether the course include any the recent version of the WaveTech, but this work was done about 2 years ago. So at the time we used the original version of the WaveTech to generate the fine tune and generate the ASL result on our data set. And this is the statistics that we had, and so we actually used this part, the bottom part, the testing part for the validation and test data set. So that was the spoken part of our data set. And we organized a public benchmark under the Tenth Dialog System Technology Challenge track using this data set as a validation and test data set. And the setup was like this. We used the previous written dialog data set as the training data set and a part of the validation data set, while we use this our spoken data set as a test set to see how the models trained on the written data set works for the spoken data set that we had. And as for the baseline, so we took the state-of-the-art dialog state tracking model. So at that time, so 3P, so that was a joint model on top of the BERT for the classification and span detection model. And 3P was used for the baseline for DST. And Novo was used for the second task, for the knowledge-grounded response generation. And that was actually the winning system for our DSTC9 track for the original benchmark on the written data set. And this is also based on the Plato 2, the pre-trained model. And that is the classification followed by the generation model. So with the single model for each subtask for our knowledge-grounded response generation pipeline. And yeah, here's the baseline result. So this is based on the models fine-tuned on the written text as it is. And you can see that there was huge gap between the result on the written test data set and the spoken test data set. So as you can see here for the task one, the Duolingo accuracy, the state-of-the-art Duolingo accuracy at the time on the MultiVoice 2.1 written test data set was over 50%. But surprisingly, that the same model worked very worse for our spoken test data set, and the Duolingo accuracy was even below 1%. So when we just use this model with no modification or no augmentation on that. And also for the task two, the performance degradation from the written test data set to the spoken test data set was quite significant. For the knowledge selection, it went down from 88% to 49%. It was huge. And also for the generation metrics, so yeah, that was went from 30 wish to the 12 or 13. So it didn't work very well on the spoken test data set. That was the observation from our baseline result. But after getting the result from our challenge participant, so yeah, we realized that the teams participated in our challenge did a great job. So you can see here this is the sorted list of the result for the task one participant, and the top the row is the winning team for this task. And you can see that the Duolingo accuracy from this the best team, the best entry was 46%. So and you can see that the baseline is the below 1%, but the highly ranked teams did a great job. And so looking at the method used in the top teams, one notable thing was that conventionally, the classification and extraction was the main method for dialog state tracking. But from this benchmark, the generation-based method were much better than the classification and extraction-based method for the state tracking problem. And this is well aligned with the recent trend, because right now we are using the generative language models for most of the tasks, so including this dialog state tracking. So this is not very surprising at this moment. But yeah, that was the key observation at the time. And another thing is that all the top 4 teams tried some data augmentation from the written text, the written data set to more spoken data-like. So and especially the top team, the A11. So this team tried 3 different data augmentation methods, including value substitution. This is the entity replacement with the alternative entity from the ontology, and dialog generation, which is to generate a new dialog flow. So in addition to the ones in the training data set, and they also tried some speech simulation. So they converted the original written utterances in the data set into the more like the ASR result. So that worked very well. So this data augmentation was another key to success for the top systems. And the other one is the model ensemble. And this is very common in this kind of public benchmark. And they trained multiple different versions of their models with different configurations. And for the final result, they just ensemble the result from the multiple models. And that helped helped to boost the performances and win the challenge. And yeah, that was the task 1 result for the dialog state tracking. And for the second task, there was about 60 entries submitted by 16 teams in total, and this is the overall result. And so here, this shows the comparisons of the participating teams' result compared to our baseline. And for tone detection and knowledge selection, majority of the teams achieved much improved performances compared to our baseline. And also response generation, especially for the response generation, the performance improvement by the systems was huge from the baseline. And that was also the same from our human evaluation result. And you can see here the top teams got about 3.5 or 3 point-ish the ratings out of 5 from our human evaluation result, while our baselines stayed about 2.7. So yeah, the gap was significant. And again, for the task 2, we observed the same trend. So the data augmentation was one key to achieve the high performances on the subtasks that we had, and also model ensemble helped. So yeah, these were aligned with the task 1 result. Okay, so the key takeaways from this DSTC10, the task track 2, was that the baseline SOTA models trained on the written data failed to address the spoken data. That was the first conclusion. And another thing is that data augmentation was a key to achieve high performances on both tasks on the spoken data set, because we have limited amount of the training data set collected from the spoken conversation. So the data augmentation is important also in the practical application, because we need to convert the existing data set into more the closer to the actual input to the spoken dialog system. And for the dialog state tracking, the generation-based method was better to handle the noisy task set compared to the extraction or classification-based method. And the ensemble helped to boost the scores and win the challenge for both tasks. Okay, and so this was this result was present. This shared and presented, and we wrapped up this track in the beginning of 2022. So it was about 1 year ago, so more than 1 year ago. And so since then, there has been so many changes and so many updates from the research field, especially with the large language models. So I think as one future direction, I think it would be interesting to revisit this task and try to see whether the latest, the state of the art large language models, how did these models work? Also for the spoken data set that we had. So that is one potential future direction. And the other direction is end-to-end approaches, I think. So now we are still using the pipeline architecture to recognize the speech, to transcribe the speech to the text first, and applying the models trained on the written text. So this kind of pipeline architecture is not very robust in general to handle the noisy, the spoken inputs. So due to the accumulated errors from the earlier component in the pipeline. So the end-to-end approach, by taking the speech directly to the predict or generate the downstream task outputs. So that may be another future direction. Okay, and yeah, I think that's it from my side. And you can find our data set and our paper from the QR code here. And so one thing is that so we have only released our the ASR result with no speech data set. The audio files are not released yet, but there have been so many requests from our challenge participants. So we have been working on internally to release this data, but it takes some time. But anyway, so once it's done and we are releasing this audio data set, so we will announce it in DSTC mailing list. So if you are interested in this data, so please, I encourage you to join this mailing list and stay tuned on the update. Okay, that's it. And thanks for listening. And I'll be happy to answer any question.
Thank you so much. It was a very interesting talk. I'm going to bring back to the screen folks from the team who were monitoring the questions and the speakers as well. And I don't think we'll keep the slide on a little longer so that people can take a picture and join the mailing list to learn more about the data and any other announcement that you may be sharing using this email list. Does anybody want to start with a question? VB, maybe you? You're muted.
Sorry, too many browsers. Thank you so much for such a brilliant talk. Seokhwan, sorry, I'm butchering your name.
No problem.
I had a question, and there were like a couple of questions in the chat. One of them was about the paper, so thank you so much for putting the QR code up there. Just out of like personal curiosity, if you were to replicate the study, say today, and I know that previously like you had sort of used the wave to vec 2 architecture, and now with the advent of sort of more encoder decoder architectures like Whisper, and also with sort of new other sort of multilingual variants of wave to vec 2 as well. What do you think, like which direction would you want to go to, or would you want to try specifically from like an architectural standpoint? And if you have any sort of insights about that, that would be great.
Yeah, that's a great question. Yeah, and definitely. So it would be worth to try the latest state-of-the-art architectures to reproduce this result. And I think so. If we release this audio data, I think that could be done by public. I think so. But the thing is that so at the time, so our purpose was to generate some the ASR result with any existing open source model at the time. And so that was the reason why we used the wave to vec, because that was the state of the art. So if I remember correctly. But so I believe that so with the advancement of the ASR representation and architecture of nowadays, so we can largely improve the WER. So we can largely reduce the WER. So because WER was quite high for our data, so that was okay for the evaluating the dialogue, the robustness of our dialogue models, but that was not very realistic because now we have much better ASR solutions. So in practice, the WER will be much lower than our settings. So it will be definitely worth to try to get some more improved ASR result and to do the evaluation again on our the dialogue models on the improved ASR result. I think that will be definitely a worse direction, I think.
Brilliant. Thank you so much for that response. I'm just looking through the questions. I think like questions right now are like a mix of the questions for the course and so on. But at the moment, I don't see any other relevant question, so to speak.
So I have a question, if you don't mind. So you mentioned different ways to augment data, and since this paper came out about a year ago, this research came out about a year ago, have you seen in the past year any new techniques to augment data that have potential to be useful to this particular case?
Yeah, so that's a great question. And so not particularly for our data set, but so this kind of data augmentation is a kind of the de facto standard right now to generate some data and improve the quantity and quality of the data set with the advancement of the large language models. And for the dialogue research field in general, so many people try to create the data set. For instance, so for Alpaca or Vicuna, so all these the models were fine-tuned on top of the Llama, but the training data set were obtained from ChatGPT or OpenAI's APIs. So that was not fine-tuned, not created by the crowdsourcing manually. So this was based on the automatically generated data set using the large language model. So definitely this kind of things will be a new things on top of the data augmentation method that our challenge participant tried. So yeah, that's the reason why I listed that as a potential future direction to revisit our task, because the large language model can do probably can do much better in both data augmentation and the prediction and the response generation themselves. So the large language model could be one thing that we can try on this data augmentation, I think.
Thank you so much. VB, do we have any questions from the audience that we could ask?
Not at the moment. There are a lot of like course-related questions. So
yeah, I've seen Sanchit has been on top of most of them. Thank you. Well, if there's no questions about this particular talk, then we can move on to our next presenter. And I am happy to introduce Paige Bailey, who has joined us today. Paige is a lead product manager for generative models at Google DeepMind. And prior to returning to Google DeepMind team, Paige spent just over a year at Microsoft as the director of machine learning and MLOps at GitHub, working on projects like GitHub Codespaces and Copilot. I'm sure you have heard of them. And as a former applied ML engineer in Azure Research, Chevron, and on NASA projects, Paige can't imagine a more exciting charter than accelerating developer productivity with machine learning and unlocking the capabilities of these models for users. So we are thrilled to have Paige join us, among other speakers, and to share her presentation. Thank you so much. Thank you so much for joining us. As usual, drop your comments and questions in the chat so we can get back to them at the end of the presentation. And I'm going to give the floor to Paige.
Awesome. Excellent.
Do you have slides?
Yes, I do have slides. Let's see. So it's asking me to upload a file. Do I need
present,
to
slides and upload?
Okay, so
we're going to give you
upload
a minute to do that, so don't worry.
Excellent, thank you. I apologize, and also I apologize as well. This is so file download as PDF document. Let's see.
That should work.
Yep. And then I am dialing in today from the London office. I'm dialing in today from the London office, which is currently where Google DeepMind or most of Google DeepMind sits. So if you see everything looking particularly beautiful today outside the window, that is because London is very beautiful today. And I should be uploading the presentation now. It is a largish presentation, so hopefully, hopefully
I see it. So I can edit it to stream, and I'm gonna remove everybody except for you, so you get the full attention.
Perfection. Thank you.
Yeah, have fun.
Excellent. All right, everyone. I am delighted to be here today. As mentioned, I'm the product lead for generative models at Google DeepMind. In particular, I was responsible for the Palm 2 launch, which we'll be talking about later in the presentation, as well as Code AI, which is our machine learning is applied to software development charter for Alphabet across both our first-party solutions as well as our third-party solutions. And what that means is that we take these large generative models, a lot of data about the software engineering process, and then also sort of apply the models through various phases. So things like code generation, of course, and code explanation, but also things like automated build repairs, performance fixes, security vulnerability detection, all sorts of things. The reason that I say this is because I have no background whatsoever in generative audio. I am helping with the Gemini model, which again we'll talk about later, and is multimodal. But I do not have experience with generative model building myself. So I've been learning a lot in the previous presentation, and I'm excited about the questions that y'all might ask. Cool. So despite me not having any background in generative audio, Google has immense background in generative audio. And what you see here is a presentation from Google I/O, which happened pretty recently, where we had Dan Deacon brought out on stage and using MusicLM to generate the pre-alphabet Google I/O show. So he and this gentleman dressed in a duck suit were able to do really, really interesting things with kind of dynamically changing the tone and the content of the music. And awesomely, we were able to release it externally as MusicLM. So if you go to this link, I am happy to put the link in the chat at the end of the presentation if folks aren't able to type it all out. But you're able to play around with MusicLM and generate your own tracks. Here you can see something called modern pop country ballad that you'd hear on the top 40 radio. And then also things like ambient sounds I would listen to by the ocean or something similar. So experiment with it, share what you've learned. It's pretty cool to be able to play with these models in real time. So as Google, our mission is to organize the world's information and make it universally accessible and useful. We've been doing this for a very, very long time. And organizing all of that information makes for really great pre-training data for these large generative models. And as a result, they've driven, in pursuit of this mission, we've driven a lot of groundbreaking work on foundational models. So both large-scale neural networks as well as sequence-to-sequence learning. Of course, the attention is all you need paper, but also things like instruction tuning and RLHF. I think the first paper or the first blog post really that I saw about RLHF was one of the DeepMind publications in 2017. So we've been thinking about the foundational like nuts and bolts of what make generative models for a really, really long time. And now it's become kind of mission critical and core to our business. We also have great infrastructure and tools like TPUs and JAX, which is an open source machine learning framework, in order to make such models and to make them scale across giant clusters of machines, including like giant clusters across data centers, right? Like being able to stitch all of these computers together and make them, run a single program is a really exciting thing to get to be a part of. And then, of course, we also have deep learning techniques. So things like Chinchilla, you might have heard of compute optimal models or Chinchilla optimal models, Flamingo, so visual language models for few-shot learning, and then also Flan fine-tuning. These are all kinds of things that were pioneered at Alphabet and are all critical components for generative models. So at I/O, we introduced our latest generative model, which is building on all of these things that we've learned in the past, Palm 2. And Palm 2 is kind of the next iteration of our first Palm model, but it included massive breakthroughs in multilingual reasoning and coding capabilities. It was built using JAX, and it's faster and more efficient due to like a broad variety of model sizes that were deployed across many product surfaces. And at I/O, we announced it was deployed in over 25 Google products. Since then, it's been more like in over 38 features and products. And honestly, like that is one of the coolest things that I have ever been part of in my career. As the lead PM for Palm 2, I was able to get it deployed into workspaces, so Sheets, Docs, etc., as well as Bard, Magi, which is our new search experience, and then also some of the ML integrations into developer tools across Colab, Android Studio, as well as some of our Duet capabilities for Google Cloud. And if you're curious about it, we put a technical paper as well as some examples and content at g.co/palm2. I'll also add a link to that at the end of the presentation. So just as a few kind of tactical examples, it has improved multilingual understanding, so being able to translate from one language to another, as well as to explain nuanced meaning in languages. So being able to understand why some translations might be miscategorized, or why some translations or jokes are funny in one language and not others. So this is really, really cool, and it's kind of a step change in terms of model capabilities compared to what we've seen before. It also has reasoning capabilities, so being able to understand placement for objects that a person might describe through text or natural language, and enhanced code capabilities. And one of the coolest things is that you can also kind of mix and match these capabilities as you will. So here you can see an example of line-by-line descriptions for a chunk of source code that you generate in Korean. You can also explain in kind of long-tail languages. So a colleague had it explain C++ like a transformer, but in Malayalam code comments. So it's really, really nice to understand, just personally how much this might be able to open up access to people who might not have English as a first language, but who are, learning how to code or learning about math or physics concepts. So that's really energizing. And as I mentioned, it's now powering over 38 products and features across all of Alphabet. Bard is powered by Palm 2, soon to be powered by Gemini. And then the coding capabilities we had already mentioned before. It looks like some of the GIFs that I might have had broke whenever I exported as a PDF. So you'll just have to trust me and play with Bard yourself. But we've also introduced recently new export actions for things like Gmail, Docs, Sheets, and then also Replit and Colab. So if you generate some Python code, you can export it as a Colab notebook, which is pretty cool. Bard is available in English in over 180 countries around the world. It's also available in Korean, Japanese, and a host of other languages. I think we've opened up to most of those 40 languages so far, but I encourage you to test it out, to see what you think, and to share your feedback. We're also, this was also a GIF, though I kind of like the still with like the dog with his tongue sticking out. But we've also introduced image understanding and also image exporting capabilities for Bard. So if you would like to generate image content, perhaps you want to understand, you're visiting Chicago and you want to understand the architecture of the city. If you ask that query, it's highly likely that you will receive images as part of the output to show you things that you might want to visit. So that's quite cool. And then also app integration. And pretty soon, also announced at I/O, we will be, we are currently in the process of training our Gemini model. It is the first model that we're training jointly as both former brain and DeepMind. And it's intended to be our most powerful yet. So you can think of it as a superset of Palm 2 capabilities, including multimodal features. And what that means is that the model can understand many different modalities. So not just text, not just code, but also music or other kinds of audio, video, images, like CAD models, all sorts of really cool things. And as a result, I think that we're going to see more and more multimodal scenarios that models enable over time, like being able to take in a Figma design and generate the code that would be used to create a functioning web app, or being able to describe in natural language the kind of Figma design that you would like to see, and having the UI generated for you on the fly. I think these are really, really cool applications, and we've only just started tapping into the potential of this So be on the lookout for more capabilities. And then demo time. So again, since I just have slides, I have kind of what it would look like if I was demoing things. And so for Bard, you can ask it to do things like creating a linear regression model in Python using scikit-learn and including a funny pun. So here it says, I guess you could say that linear regression is a pretty straightforward model. I agree. And then you can also investigate other drafts that you might include so that, model outputs are not deterministic. So you can see like different flavors of output responses that might have been generated. And then also kind of these export capabilities. And then you can export the Python code to Colab and run it. So being able to kind of see these things in real life is very, very cool. And we've also incorporated machine learning features into Colab, though I think those are still yet to be released fully externally. So you can play with the same models that are used to support Bard directly within your Colab notebook for code generation, for error explanation, for automated error fixing, all sorts of things. Yes, powered by Bard. Excellent. And then with that, I would like to say thank you to everyone. Thank you for having me. I hope this was useful or meaningful or interesting. I think music and audio generation is one of the coolest use cases for generative models by far. As a person who used to spend way too much time lurking as a DJ in her college radio station. So I am excited to see what you build, and please feel free to ask away.
Thank you so much. I'm going to get everybody back to the stream. Right. Are we all here? Yes, we are. I have a question to kick things off, actually. So, given your vast experience with applied machine learning, so you work at Microsoft, Google, GitHub, Google DeepMind, and so for a lot of years. And during those years, a lot of things from the perspective of technology have changed. So we've got new model architectures, better hardware for training, more data, and all kinds of things. But I wonder if you find, if you can name something that is consistent, and rather what skills would you say people should invest into that are going to carry them through all the turbulence of new tech and new approaches, new capabilities? What is the constant thing that's going to help people in the long term?
That's a great question. And I think I started doing machine learning in 2009 when the world looked very different. So like I think the majority of the models that we were working with were really things like linear regression, support vector machines, like decision trees. Those were the thing that everybody was interested in. And I have to say, like it's right now we're living in such a state that I've waited my entire career to see it. Like this, it finally feels like we're truly on the path to integrating AI into everything that we do, and really making it real for everyone out into the world. Some things that have stayed consistent are that you still have to care about data quality. There's this kind of myth that for training these large generative models, you can just throw whatever you want in the pre-training data mixtures. There's so much data that the model kind of discerns signal somehow, even with all of the noise. But for instruction tuning, for domain-specific fine-tuning, so like if you're doing continued pre-training on source code, those sorts of things, data quality matters immensely. And I think that's part of why, if you look at kind of the data set that was released with Anthropic's Helpful Harmless Assistant paper, that data is just so impactful for building building great chatbots, building wonderful experiences. So you always have to care about the data. And then in terms of just like being a solid human, like being able to ask good questions, being able to collaborate effectively, and also being able to communicate what you do is mission critical and important. Like the algorithms, the techniques, the libraries, the frameworks, they're all going to change. They're going to change constantly. Like they haven't stopped changing for a while, and I don't think they're ever going to stop changing. But the importance of high quality data sets and the ability to kind of work with people, understand where the gaps are, and collaborate effectively and communicate what you've just done are all kind of they're never going to cease to be important.
Absolutely agree with you. VB, do we have questions from the audience?
So there are a bunch of questions about how can people access Palm 2 and Gemini like models, and would there be like a public access, or would they be open source? If they're open source, then we'd definitely be more than interested.
Awesome. So right now, Palm 2 has been released across a lot of different product surfaces. So, I think I mentioned if you go to Bard, you can try it out as the underlying model powering the chat experience. If you'd like to try it out in API form, we have made it available via Vertex AI. So all you have to do is look for the Palm API. There's also a developer API. If you don't feel like paying, that is free of charge. However, all of the inputs and outputs are kind of used for additional, for understanding purposes and model improvements. So I would not recommend using the developer API with any data that you hold close to your heart and don't want anybody to use for purposes that are not your purpose. But the Vertex AI APIs are you can remain like secure in the knowledge that your data remains your data, and that any inputs and outputs will not be used to improve the model over time. But those are the best ways to try it out, both integrated directly within products as well as the APIs that we've made available.
Brilliant. There was another question about multilingual data sets for instruction tuning. So I'm just going to rephrase it. What's been your experience sort of dealing with instruction tuning, especially for like these really large language models, such as Palm 2 and so on, and more specific to like how to get like a better performance for say multilingual side of things?
Absolutely. So this is a wonderful, wonderful question. Instruction tuning is a really challenging thing to do well, and I think it's an art. Like if you can figure out how to do it, it's one of the things that can move the needle the most for performance for your model. There will be instances. So say you train a generative model, you can do generic instruction tuning. However, that model will not probably like if you do instruction tuning just in English language, then the model will probably forget what it learned about all of the other languages. Like it'll still be able to generate, Korean or Spanish or something, but it won't be quite as good. So as you're building out instruction tuning sets, if you have a model that supports multilingual capabilities, definitely investigate multilingual instruction tuning. And then also, if you are dealing with a model that is, say you're trying to build a chatbot about code stuff, you should also probably do code instruction tuning. So your instruction tuning set should not be generic, like a regular text generation model. It should include questions about code explanations, code generation, etc. And that is very, very important. Even if it's like say you want to generate or you want to create a model that's very, very good at answering questions about like Android devices, your instruction tuning set should probably be about Android use cases. And that's, we're all kind of building the plane as we fly it, right? Like we're all, kind of learning through what we experience users are asking these models. And over time, you can get kind of a distribution of these are the kinds of questions that people ask. These are the kinds of things that they're interested in. These are probably the distribution of things I should be including in my instruction tuning set. But at the very beginning, it's just guesswork. And then afterwards, it's data science. And you should be like using all of the great questions and feedback that your users are supplying you with to understand what your instruction tuning set should be.
Fantastic. I cannot find. Well, there is actually one question. It would be interesting to just know your take on this more from like in more from your product manager sort of hat on, and more from like how you see the industry, which is like how do you see these sort of generative sort of music, and also like pretty much any generative model sort of see affecting like the larger industries in the future or like currently, and specifically for music, if you've seen any like creative use cases maybe internally, and so on, if you want to talk about that.
Yeah, I think one of the things that I'm most excited about is I am a huge fan of indie games, and indie games are usually labors of love for everybody involved. You might have one person that is attempting to, like, with blood, sweat, and tears, make a game, or even just like a small handful of people. And even if you're a software engineer or you're a person who's really gifted at being able to create or design the playing experience of a game, or the generative approaches for some of the characters, you might not be the kind of person that's great at art or great at like music generation, like composing what the sequences should be. So one of the coolest things that I find about models like MusicLM is that you can describe, like, perhaps your character's about to face a boss in like the final level of the game, and you describe like what kind of emotions you want the player to be experiencing as they're like fighting this boss character. I could not compose such a thing, but I feel very grateful that if I built such a game, there is a model that could help me get to the kind of in-state experience that I would like to enable for my users. So those are the kinds of use cases that I get most jazzed about. Not so much the like, how do we create the next like top 40 single or whatever, but how do we empower people who are really, really gifted at like, perhaps 60% of the things that would be required to produce something. And then oftentimes like the required 40% else friction means that their game never gets released. How do we get them over the line such that, these people can get their ideas and their creations out into the world? So that's kind of like, I don't know if that's a good answer, but like that's the kind of stuff that gets me most excited about these models.
I think that was brilliant, and like oftentimes when we look into these like music models, be it MusicLM, be it sing song, and so on, like we try to sort of relate it to oh my god, this is going to be like the next AI singer out there, and we're going to have like top 40 tracks or top 100 tracks and so on. So this also like sort of sets context about the fact that there are other creative use cases for such models, and it's not really displacing anyone. Yeah, and so on. Thank you so much.
Absolutely. Thank you for having me. I think we're almost at time, or might be a little bit over. So
yeah, I think we should move on to our next speaker. And if everybody would like to hang out a little longer after our last talk, we can still talk about music generation and audio AI and all the new models and architectures and whatever else, career development, learning topics that we want to cover. But at this point, I think we should say thank you to Paige for her talk and give the stage to Brian. I'm going to bring your slides to the stream. And
we got slides. You can hear me?
Yes, we can hear you. We can see you. We can hear you. We can see your slides. That's great. Everything is working.
Perfect.
And Yes, so your talk is going to be on Librosa, and it's a package that we also use in the first unit of the course to help learners discover data and understand audio data a little bit better. And so happy to give you the stage to give an introduction to audio processing in Python.
Great, thanks. It's great to be here. Even though I'm in my office, it's great to be here with you all. I am going to be talking about Librosa, kind of giving you the context, what it does, what it's not really intended to do, and how it can fit into your workflow. But afterwards, I'm totally happy to talk about all the other topics because there are a lot of fun things to talk about with audio and machine learning. So, very big picture, Librosa is just meant to be tools to make it easier for you to work with audio, primarily for a scientific context, which is what I care about. I've seen a few questions in the chat during this event for the last hour where people were kind of asking, like, why is audio so much harder to work with than, say, text or images? Hopefully, in the course of this talk, you'll get a feel for why that might be the case. And Librosa is really meant to attack that particular problem. So it's not meant to be a machine learning package. We assume that TensorFlow or Torch or scikit-learn or whatever can handle that problem for us. What we're trying to do is give you wrappers that make it easier to get your data into a machine learning model, take the results out, make sense of it, understand what's going on in your content, and do something useful. So that's big picture where this started. And I've been at it for about 10 years. And at this point, we have over 100 contributing developers, and it's fairly mature. So I'm going to give you kind of the overview of how the package works and just kind of the highlight reel. So just from the start, some design principles. This is meant to be function-oriented. So think NumPy, not class or object-oriented like scikit-learn, right? So if you're familiar with NumPy, everything should feel pretty familiar. Everything is function-oriented, data comes out, data goes in, data comes out. Pretty easy to use. One of the things that you'll find when you work with audio data, especially if you're looking at code from different developers or different research groups, is that there tends to be a lot of divergence between the ways that people implement things. So we spend a lot of time trying to make everything kind of internally consistent and work well for the average case, which for me means analysis. If you're interested in generative models, our default settings may not be the best for you, but we do try to make it easy to change things and make it pretty clear what's going on and how it works. The package is meant to be sort of understandable and simple and well documented. So as much as anything else, it's meant to be a learning tool. You should be able to crack things open and see what's going on, maybe with a little bit of work. For that reason, we focus on simplicity and stability and kind of off-the-shelf methods. We're not looking for like the latest and greatest model because that's going to change every couple of weeks at this point. What we want to do is give you tools that are easy to use and easy to control. And you can either use those as part of your workflow or maybe as baselines. So that's kind of the scope here. We hope that you take this stuff and use it to make things that are better. That's the entire goal. So I'm going to give you a quick tour. Most of the stuff is taken directly from our documentation site. This link should be easy to find for you. I'll give it again at the end. But I'm going to walk through sort of the main modules of the package. So I've broken this down into sort of 4 major parts, and then within each of those, there are a few more specifics. At the top level, we have what I call general purpose tools and general purpose packages. And these are things that apply to pretty much any kind of audio analysis. And this is what I'm going to spend most of the talk covering. Next level down, we have things that I think of as music related, but you see there's a little star there. And that's because sometimes you find use cases for these methods that are outside of music. So things like event onset detection, temporal segmentation, those can generalize to other types of audio analysis. So maybe like bioacoustics problems, environmental sound recognition, maybe even medical applications sometimes use things like beat tracking, if you think like heart rate monitoring, that kind of thing. These methods can be generalized a little bit. But these you should think of as slightly more specific analysis methods. We have another couple of modules that do things that specifically modify either signals or representations of signals. And this you can think of as being useful maybe for like data augmentation techniques like we saw mentioned in the first talk. I use this kind of stuff all the time to do things like time stretching or pitch shifting or other sorts of slicing and dicing of audio signals to make my data set a little bit richer. We have other stuff than those specific methods, but those come up a lot. And then we have some helper functions. I'm not really going to cover these, but if you spend some time reading through the source code, you'll kind of get a feel for what might be useful for you. So that's sort of what we have entirely in the package. I'm going to focus on these purple modules at the top. So I'll give you a couple of code examples, and you can sort of see how things fit together. So the main part of the package that people run into when they first come to using it is the core module, and anything that's in core is going to be re-exported as librosa.star. I'll show you some code examples in a moment. But these are things like ingesting audio, maybe doing stream processing of audio, synthesizing signals. Maybe you want tones or chirps or clicks or whatever for whatever reason. You have all that kind of stuff just sort of ready to go. Then we have what I would consider to be low-level frequency domain transformations. A lot of people think, yeah, we have the Fourier transform, we don't need anything else, and that is definitely not the case. We have many different types of time frequency representations, and I'll show you some examples of what that looks like. Sometimes they're better suited for one application, sometimes better suited for others. We provide many options for that. We have an absurd amount of code dedicated just to handling unit conversion, which seems like a simple, basic thing, but it's really easy to get the details wrong. So it's probably not the sort of thing you should be doing yourself. But think about things like converting between different time units, different frequency units, maybe converting hertz to MIDI notes to music notation, either Western or maybe Indian notations. We have all that stuff in there. So definitely use that if that fits your application. And then we have a bunch of other sort of what I would call various DSP or digital signal processing functions. And these have to do with like maybe estimating the fundamental frequency or like the base pitch of a monophonic signal, maybe phase retrieval methods. If you're, say, building a generative model to model a spectrogram and you want to estimate what the phase should be to reconstruct the actual time domain signal, you'd use some of these methods. There's a bunch of other stuff in there. And this goes on and on. You can explore the documentation site well on your own, and you can lose lots of time to that. But to start with, I'll give you just a little example of what sort of a hello world for Librosa would look like. I'm not going to play this audio sample, but this is an audio recording. It's a few seconds long, and this is something that ships with the package. And we have a load function. And what load does is you give it a file name, and there are some other options to it. In this case, I'm using mono equals true. And what this does is if your audio file is stereo or multi-channel, it will downmix it to a monophonic signal, so single channel, just so you have a single time domain that represents air pressure varying over time. By convention, we're going to call that Y. So think Y is the vertical axis over time. That's what our audio signal is. And it's also going to return the sampling rate of the signal. And this tells you how many samples per second we have. So the default sampling rate that we always remix to on load, and I'll come back to this at the end of the talk, is about 22 kilohertz. And this is fairly standard for analysis tasks. What this means is that every second you have 22,000 numbers. And right away you can see that this is already very different from what you might have in text, where an entire sentence might only be, a few dozen tokens. Here we're already in the scale of hundreds of thousands. And this is what makes things like transformers a little bit unwieldy with audio. So anything you can do to make the data a little bit more amenable to analysis is going to be useful. So we have our Y, we have our sampling rate. Usually the first kind of thing that you might do is transform this into a spectrogram. Spectrogram is sort of a catch-all term for anything that shows frequency content changing over time. And the fundamental unit of that, or the sort of introductory version of that we usually see, is called the short time Fourier transform, STFT for short. And that is a function that just takes time domain signal, and you give it some parameters that say how many frequencies or how many samples you want per frame of analysis, and how many samples you want to hop from one frame to the next. The result of this is going to be an array called STFT, which I have in purple here. This is going to be a complex valued array. So the rows correspond to the different frequencies. So 0 hertz sampling rate divided by NFFT, twice that, 3 times that, up to what we call the Nyquist frequency, if you're familiar with this idea. The columns represent different time steps, and the values in this array are complex numbers, which encode both the magnitude, the amount of energy at that frequency, and a phase offset, which is basically like a delay within the frame. What would you need to shift a sine wave at this time step to make it line up with what we observe in the signal? Usually we throw phase out for analysis purposes and just focus on magnitude because that encodes a lot of the information, especially if we have overlapping frames. So the output of this object is going to be about half as many frequencies as the NFFT number here. 2048 becomes 1025. There are reasons for this. If you want to know about it, ask me afterwards. And the frames are now significantly reduced, right? So frames corresponds to time, but we're skipping about 500 samples at every step. So we had a signal that was about 117,000 samples, divided by 512. Now we have 230 frames. Now you have something that's a little bit more tractable to a machine learning sort of task. So this is just a very short example of what it looks like to load in a signal and do some basic analysis. But usually we want to do a little bit more than that. So we give you some methods that help visualize things. And these are built on Matplotlib, but sort of adapted to make things work really well for audio. If you've ever tried to plot a raw audio time series, the longer it gets, the harder it is to see any information. So we have a function called WaveShow that does some nice adaptive sampling tricks to make sure the signal is still visible and interpretable at different timescales. That's here on the left. And then we also have this ridiculously overpowered function called SpecShow, which was originally developed for visualizing spectrograms, but it does a lot of other things as well. And I'm not going to spend hours going into all the details of how that works. But the gist of it is that this gives you sort of a good default starting ground to understand what's going on in your signal. So had I played that signal, you would have heard a trumpet run that's just doing a little, I think it's F Dorian sort of run. Over time, it would look like this. One of the things that we often do when visualizing spectrograms is convert the raw energies into a decibel scale. And the reason for this, there are a couple of reasons. One, it corresponds to how humans perceive differences in energy. But two, more practically for our purposes, if you don't do that, the whole screen looks black and you don't really see any content. When you log scale this to convert it to decibels, you can actually see some content in the signal. So generally, I recommend doing this whenever you're trying to understand what's going on in your audio data. So I've thrown around a few terms without really defining them properly. So I'm just going to take a second to do that here. So first term, a sample. And this is a measurement of a continuous signal, like my voice going into this microphone right here. We're going to measure that signal at regularly spaced intervals. And that sequence of measurements is our signal. So this is a discrete signal. A sample index, let's say we have a sample index n, corresponds to the time where n is divided by the sampling rate. So if you work through the unit analysis, do your dimensional analysis on this, this number will come out. Samples divided by samples per second gives you a number in seconds. A frame is a slice of the array containing a fixed number of samples. So in the previous example, we had 2,000 samples per frame, give or take. Sorry, it just started raining very hard here in New York with some thunder and lightning. So hopefully that's not coming too much through in the microphone. But for example, in this picture, each of these purple boxes corresponds to a frame. And usually the length of the frame is the same as NFFT, but not always. Not everything is Fourier based, but that's, if you're thinking that, you're most of the way there. The hop length, this is the number of samples between adjacent frames. Sometimes this will be called stride, sometimes it'll be called frame advance. Sometimes it might be parameterized differently in terms of overlap between frames, but it's all the same idea. It's how much you move from one frame to the next. And just a quick note, in Librosa, we always center our analysis windows, and there are technical reasons for this that I won't get into. But the idea is that the nth frame is going to be centered around the sample indexed at n times the hop length. Okay. Quick second example. Basically the same code as before, but what happens if we don't want mono? What if we want to do stereo analysis? Or what if we want to analyze a batch of audio signals? Something like that. We can do that. We just say mono equals false. And now we have a new array that has the same length in terms of samples, but now we have two channels. And pretty much everything else in the package will just work in the way that you might expect if you're familiar with things like Torch or TensorFlow, where we just have these multidimensional arrays that just sort of fan out in the way that we expect. So nothing really to worry about with this. The conventions for data layout here. The trailing axis, the last thing you see, is always something like time, whether it's samples or frames. The leading axis is going to be channels, if it exists. So if we have a stereo signal, Y of 0 will be the left channel usually. Y of 1 will be the right channel. And if you have more than that, you can just keep going. And you can use the ... notation in NumPy to just slice out all the dimensions up to that. And anything in between the first and last channels is going to correspond to like a feature dimension. So it could be a frequency, it could be something else. So if you do a multi-channel short-time Fourier transform, the first channel will index which of the signals we're talking about, left or right. Second dimension will correspond to the frequency, and then the last dimension will correspond to the time. And if you've done a bit of this kind of thing with images or videos or something like that, this should be fairly familiar. Okay, so that was sort of the basic stuff. We have a bunch of other things that I'm not going to have time to get into too much detail with here. But the main thing that you'll probably run into is the feature module. And we provide a lot of feature extraction methods for different kind of applications. The main one that you're likely to see is a MEL spectrogram. And this is essentially taking the frequency axis and then interpolating it on a logarithmic scale so that every octave displacement is equally spaced from the previous one. This is a very good thing if you're using something like a 2D convolution. You want your convolutional filters to cover the same effective frequency range. If you don't do a log scaling, then the ones at the bottom are going to cover a much bigger range effectively than they would at the top of the image. So for that reason and many others, MEL spectrograms are very popular. The rest of these I don't really recommend unless you know what you're doing. If you're doing music types of things, you might want to look at chroma features, which collapse things down to a pitch class grid. So rather than having frequencies, we have notes. So we only have 12 dimensions here corresponding to the chromatic scale, C, C sharp D, D sharp E, ... And these can be useful for things like chord recognition or maybe audio fingerprinting, things like that. We have some features for analyzing tempo and rhythm and that sort of thing that follow a similar sort of trajectory. I expect those probably won't come up too much, but MEL spectrograms definitely are a good starting place for most applications. So I recommend you look at those. We have some functionality for sequence modeling. So things like path alignment. If you have two versions of a signal, maybe one is faster than the other, and you want to figure out what time spots correspond to each other. We have functionality for that. We have functionality for looking at recurrence analysis, segmenting songs, that kind of thing. And one that you might want to look at in a little bit more detail for your applications, if you're doing something like time varying classification, maybe event detection or speech transcription or something like that. We have a bunch of helper utilities for Viterbi decoding, which are really handy to have around just to make it easy to sort of post-process and smooth classifier outputs so that they don't flap from one frame to the next. This is a very useful utility to have around. Okay, so I'm going to leave you with some tips and tricks just to effectively use this stuff in your own practice. First one, if you're doing machine learning with audio, oftentimes you want to construct mini batches for doing stochastic gradient descent. And when you're making mini batches, you want your signals to be all the same length. And that's often not the case with audio. So you need to extract fixed dimensional patches. So you can do this by hand, and it's totally doable, but it's kind of a pain. It's easy to mess up, and it's easy to blow up your memory if you do it wrong. But it turns out that if you're a little bit clever with it, you can actually use the underlying frame slicer that we have for spectrogram generation to just slice any sort of object. So here I'm using the frame utility function to make patches that are always 32 frames long and advancing by 16 frames out of an arbitrarily shaped spectrogram. And now if we had 128 frequencies by 230 frames, we do this patch generation. We have now 128 frequencies, 32 frames per patch, and now we have 13 patches. And now you can sample from this to make your mini batches. And this all operates without making any copies of the data. It's all in place. Very convenient, especially if you're doing training on very large data sets. This is a good trick to have around. More high level, this goes back to something that Paige mentioned in the previous talk. There's no substitute for having good data and for understanding what your data is. And that's what Librosa can be very helpful for, is just getting a feel for what these numbers actually mean. But you do need to understand a little bit about what it's doing to your data. So by default, Librosa will resample any audio signal to a standard 22 kilohertz sampling rate. And I get a lot of flack for this, but I still think it was a good choice because it makes the API design a lot simpler. We have a blog post explaining why we did this and how it works and what you can do if you don't want this particular default. But knowing that that's happening can save you some headaches down the road. Given that, actually understanding what the dimensions of your data mean and correspond to in terms of like time or samples or frames or any of that sort of stuff, that can help you in designing your model architecture. Let's say you want to build a ConvNet and you know that the event that you're trying to capture only really lasts for at most half a second. It's never bigger than that. You can sort of use this sort of thinking to think, okay, how big of a filter do I actually need in my first few layers to actually cover the event that I'm trying to model? Knowing this and having an intuition for what your data layout is can be very helpful in architecture design. So I encourage you to think about these things. Some common pitfalls that I see people do. I'm not going to touch on all of these. Let's see, which ones do I want to cover the most? I'll take the bottom two. First one, trying to do everything end to end from raw audio samples and bypassing any sort of analysis or spectrograms or anything like that. That can totally work. It is fine to do that. However, it usually requires a lot more data to get the same performance at the end. And what you end up with is not usually that much better than just using a spectrogram representation that you already understand to start with. Sometimes it can be better in some situations, and certainly that is the direction that the research community is going. But if you're data constrained or resource constrained, try to think about using some clever features that make your model a little bit easier to fit. It will save you some time. Parallel with that, relying too much on the default parameters. As I mentioned at the beginning, our defaults are sort of a baseline that's kind of tuned on average to work for most applications, but they might not be the best for your problem. So it is good to spend some time understanding what the parameters of the analyses actually do and whether or not they fit what you're trying to do with your model. And this just requires some domain knowledge and a little bit of experience, but it is worth the time to learn these things. So I'm going to stop here. I'm going to leave a couple links on the screen. The first one is the Librosa main website, and that'll point you to documentation, discussion forum, etc. Second one is our GitHub repo. If you have problems or bugs or whatever, if you want to make contributions, go there. And the third one is a link to a free textbook that I wrote for my signal processing course, which just gives you a little bit more background on what fundamentally all of these operations are doing, something like a Fourier transform or sampling or et cetera, et cetera. That's all covered in gory detail in that book. So I will stop here and we can have questions and hang out and chat. So thank you. Maria, you are muted.
Oops. I knew we would have some audio issue at some point because it's an event about audio. So there I was muted. Yes, what I was going to say that I'm going to leave the slide for a little bit longer as I bring folks back. Right. So let's see if we have any questions. And I think I'm going to start with the first one that's rather easy. I hope it is. But how did you come up with the name for Librosa? It doesn't really sound like audio, well, at least to me. So there must be a story behind it.
So the story here was I just finished my PhD and I was starting a postdoc in a lab called Librosa. And that stood for the Laboratory for Recognition and Organization of Speech and Audio. This was Dan Ellis's group at Columbia University over 10 years ago now. Hard to believe it's been that long. And part of the idea originally was to sort of consolidate a bunch of scraps of code that had been kicking around the lab and sort of hand it off from one grad student to the next and tweaked a little bit every time. Just to sort of bring that all in and make it internally consistent and make it sort of the package that the lab uses. So if we had Librosa, the library for the lab should be Librosa, following in the grand Unix tradition of naming things lib whatever. Now that lab no longer exists. Dan is off at Google, still doing audio research and lots of great stuff. But the package is still around, so hey, software can live for a while.
Yeah, it's a nice backstory too. We've had some questions in the chat. Also, a lot of Librosa fans in the chat.
Thank you.
Let me just quickly bring up the chat and see. So here's a question. Do you have any tips on making feature extractions work on videos with audio using Librosa?
Yes. So gory details. The way that Librosa loads audio, it sort of multiplexes over 2 different packages, and those in turn multiplex over a bunch of different libraries to do the different decodings. The default one that we use is libsound file, SND file, which does not do video, but it is faster, more stable, more reliable, etc. As a fallback, if you have a format that sound file can't handle, we'll use a package called audio read. And one of the things that audio read can do is kick out to FFmpeg. So if you have, say, I don't know, a video you've downloaded from YouTube. I don't know why you would ever download a video from YouTube. Nobody does that. But let's say you did that and you wanted to extract the audio. You could just say librosa.load video file, and it will just pull out the audio stream using audio read. So you don't have to work too hard to make that work. But it won't be as fast as if you first extract the audio signal using a tool like SOX or something like that, or even FFmpeg on the command line, and then use sound file to just parse the converted audio stream. That's a slightly more stable way to do it. But otherwise, there's no problem with working with video files.
There is a very specific question. You have the rainbowgram phase and mag in one spectrum. Is there any plan to add an inversion for the rainbowgram?
There is so in one of the things in the documentation site is a section called advanced examples. So every function in Librosa has example code where you can just copy paste and get something that works. But the advanced example is a gallery of more kind of intricate examples that do a lot of different things, showing off different pieces of the library together. And one of those is rainbowgram implementation. Rainbowgrams, if you're not familiar, they're a visualization that try to show both the magnitude and the phase structure of the signal. Usually when we see a spectrogram, you're only seeing the magnitude. The color in a rainbowgram corresponds to phase offset. So they take a little bit of training to learn how to read. They're a little bit difficult to work with, and they can be, there are subtleties to making them work with different kinds of time frequency representations, whether it's a short time Fourier transform or a constant Q transform, a variable Q transform, or whatever it is. The example notebook that we give you should be adaptable to those different situations, but there are so many different ways that you might adapt them that we haven't really figured out a clean API to just make that a visualization mode in itself. But if you want to undertake that, we would be glad to have it. So please open an issue and we can talk about it.
There's a question about analysis, and I thought I'd just bridge a second question on top of that. So you mentioned how with the rainbowgram, it can be difficult to learn how to interpret these. Is it also a case that through familiarity with spectrograms, you also have an idea of, like, you can look at a spectrogram and you can kind of understand what's going on under the hood? And there's a question of, do we always do analysis in monochannel to get to the point of using a spectrogram?
Sure. So I'll take the second question first. The answer, do we always use mono? No, but oftentimes we do, usually because there's a lot of redundancy between a left and a right channel in sort of an arbitrary audio signal that you might want to analyze. However, there are situations where having multi-channel audio contains a lot of information that you care about. Mostly those have to do with localization. So if I want to know that I'm hearing an event like, let's say, a police car driving by outside my window from that direction, you kind of need 2 channels to distinguish, like, this is more on the right side than on the left side. And those are situations where you would want to preserve the separate channels all the way through your analysis. But if you just want to say, is this a police car, yes or no, you usually don't need stereo for that. But we support multi-channel all the way through the stack. And then the first question, quick reminder.
About reading, interpreting spectrograms.
Yeah, this was, I remember when I learned to do this in grad school, it was so much fun. I just stayed up all night with a couple of friends of mine, just like loading up our favorite songs and looking at spectrogram visualizations and trying to understand what was going on. If you've never done that with Aphex Twin, I highly recommend it. It's if you get the analysis parameters right, super cool. Equation track, definitely worth it. But certainly you can learn to identify a lot of things in a spectrogram just from looking at a picture. Human voice is usually pretty easy to pick out, certain kinds of instrumentation. I've known people that can do the same thing by looking at MFCC plots, which is totally mind-blowing to me. That is not a skill that I ever hope to develop, but it's possible, sure. And this is why like training ConvNets on spectrograms works and makes sense, right? Because it's all just patterns of spectrotemporal energy.
And as a follow-up to that, if you were to take a model and train it on just raw audio, do you think it learns basically the same features that like a convolutional based model would get from spectrograms? Are we like implicitly going to spectrogram to find a representation, or
more or less? Yeah. Most of the time, most of the examples I've seen where you do this end-to-end learning from the time domain, usually if you look at the first layer filters and you organize them the right way and clean them up so they're not just totally garbled and noisy, they tend to be things like either just sinusoids or approximately sinusoids, or spikes to catch your impulses, or things like Gabor wavelets or gamma tones or other things that are sort of well understood in the signal processing literature. It tends to be the same kind of thing, except you learn a subset of those that actually capture the data that you trained on and not all possible signals everywhere, which is what a Fourier transform would do. So you might get a little bit more efficiency, but usually not more representation power.
I just wanted to jump in to read one of the comments that we got in the chat, and that is, "Thank you, sir. After 5 years of audio work today, I got answer why we use mono-channel. Thank you."
Cool.
So awesome. Do we have any more questions? Sanchit, do you see any more questions that we should?
I think there was some general questions kind of about what the best way of learning about Librosa is, about docs. If someone has used Librosa before but wants to practice a bit more, where would you advise they go, Brian?
Yeah, I would start with the documentation site. It's pretty thorough, I think. I'm probably not the best person to ask that of because I maintain the thing, but there are lots of examples. And I think probably the easiest thing to do is pick a simple task, not like instrument classification, but like, I don't know, tempo estimation or pitch tracking or something. Maybe pitch tracking is a little bit too much, but pick something simple, start from the example code that's in the galleries and the documentation strings, get something that works, and then start to pick apart what each of those functions does and what happens if you tweak the parameters a little bit. And that is a pretty good way to get a feel for how this stuff all hangs together and what it does.
Maybe the book that you mentioned can also be helpful in exploring and learning. And I should say that we have added it to supplemental resources to the first unit of the course. So if you're going to be going through the course, you're going to see the book in the supplemental resources as well. I think at this point, it is time to start wrapping things up. I'm going to thank you so much for the presentation. It was really interesting. And thank you for maintaining the package and writing awesome documentation on top of it, and books, and just explaining things to us. I have one slide to finish things today. So these are all the important links that are relevant to the course. And the course is already live. The first couple of units we have published today. And that's the first link on the slide. The second link is the link to sign up for the course updates and news and events and things like that, so you don't miss a thing, because we're going to be releasing the course, as I mentioned before, weekly. So units are going to be published every week. And of course, everybody should join our Discord, where we will be helping with questions and where you can discuss your ideas and brainstorm and learn from each other, as well as helping each other, getting inspired, getting into discussions. I'm going to drop these links also into the chat. Just a second. There we go. The links are there. Once again, thank you so much for joining us. Thank you to our speakers who have presented their very captivating and illuminating talks, which I'm sure are going to be useful for everybody who joins this course. Thank you for everybody who stayed all the way and asked questions and engaged with us. And I'm looking forward to seeing you on Discord channels and interacting with you, answering your questions, and have fun. Let's build something awesome. Take care. Thanks so much for joining.